We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Okay, so very good morning, friends. Today we are going to see JPEG image compression. So in our previous sessions, we have already seen what is image compression, why we need image compression. So let's quickly go through that part. So very first is, we know that if you just store an image, and let's say if the image is of 8-bit, okay, it's a it's let's say grayscale image of 8-bit, and image size is let's say 10 cross 10. So 10 cross 10 means total 100 pixels. Each pixel is having the total width of 8-bit data. So that makes total 100 into 8, 800 bits. That is total 100 into 8. That many 100 bytes of data is there. So that is the size of that 10 cross 10 image is 100 bytes. So you can just see that 10 cross 10 is a very, very, very small image, but still it occupies 100 bytes without compression. So that's why, just imagine if we are having let's say 1000 cross 1000 image, 2000 cross 2000 image. Let's say if we are having a video, and in each video we know that in each frame in 1 second approximately, let's say there are 15 to 20 to 25 frames are there. If it is a color video, then in each image each pixel is having let's say each it is having 3 planes, R, G and B. So there is a whole lot of byte of data. So you need to store a lot of information, and this much memory is a problem. So that's why there is a need of compression. Now if you talk about compression, what are the basic flow? It is very simple. You just capture an image through the acquisition algorithm. After the image acquisition, you just pass it through the encoder. This encoder will do the encoding process. So encoding is basically a compression. So what it does is it identifies the redundant information. That redundancy can be of different type. It can be coding redundancy, psychovisual redundancy. It can be the other type of redundancies also, which can be eliminated. So once you compression is basically identification of redundant information and just elimination of that. And once you remove the redundant information, whatever is remained is your exact data, with the help of which you can reconstruct the original image. If you do not pass that information, then also from the receiver point of view, you can reconstruct it. So that is the basic concept of image compression. So in image compression, you should have an image, then the encoding algorithm, then there is a bit stream, that is a binary data which is communicated. At the receiving end, what you are doing is you are simply performing decompression, and after the decompression, you are generating the decoded image. So this is how the compression takes place. Now, there are different encoding algorithms. So generally in these encoding algorithms, the basic goal is to identify the redundancy. So what we do is we identify the correlation between the pixels, because we know that image is highly correlated info, highly correlated. Correlated means each pixel value is depending on others. We know that in image, if you just remove one particular pixel value, it doesn't mean anything, because the information which is stored in image is stored by a whole lot of pixels. There are so many neighborhood pixels whose values are interdependent. So there is a very good correlation. So what we need to do is you need to reduce this correlation such that the information is preserved. That is also one of the concept of image compression. Okay. Now sometimes there are 2 types of algorithms, lossy and lossless compression. So when you talk about lossy compression, the quantization plays one of the important part. It is one of the integrated part of encoding algorithm if it is a lossy algorithm, because once you do the quantization, it is irreversible process. You cannot go back. Means let's say your value is let's say 1.5. If you just round it off to 2 or 1, then you cannot, at the receiver side, if you get 2, then you cannot say whether it was 1.5 or 1.4 or 2.2 or 2.1. So once the quantization is done, it is almost irreversible process and it is impossible to reconstruct the original data. So quantization ensures that it is completely the irreversible process, means it's a lossy compression. You are not going to get the exact data whatever is there at the transmitted side. So that's why, this is why basically the two types of compression algorithm are divided, lossy and lossless. So this is the basic flow. You will have an image, you will reduce the correlation, you will perform quantization, then the source coding will be done. This source coding is basically different algorithms like Huffman coding. You can also go with arithmetic coding. You can go with LZW, that is dictionary coding, and there are other coding schemes also. Okay, so these are the different coding algorithms that one will apply. And finally, after applying those methods, you will have a binary bit stream that will be transmitted. So this is what the encoding algorithm is. Okay, and at the receiving end, you need to go with the reverse process. Now here, in this particular session, we will be focusing more on the JPEG compression part. So I will just skip this part. This is all the things that we have already covered in previous sessions. So we will be directly moving on to the JPEG compression. So let's start with JPEG compression. We all know that we are using the images in our day-to-day life on social media, Instagram, Facebook, WhatsApp, everywhere, in our computers, mobiles. Now, whenever we store an image, whenever the camera captures an image, automatically it has an inbuilt hardware which gives an impact, right? Which can directly store the data into the JPEG form. Means what? Inbuilt compression algorithm or hardware is there, which is already developed. It is a standard. So therefore, now we need to understand how this JPEG compression is going on. What are the basic steps which are involved in this JPEG compression? So let's see that part into this particular video. So very first is, in case of JPEG algorithm, these are the basic steps. The first step is you divide the entire image into 8x8 blocks. This is a block-based compression algorithm. So therefore, your entire image will be divided into the blocks, and each block size is, let's say, 8x8. Then you will start from top left. You will go from left to right. Then in the next row, left to right, next row, left to right. So you will be working from left to right, top to bottom. DCT is applied to each block. So let's say there is an image. There are different 8 cross blocks. In each block, we will first of all apply the discrete cosine transform. So here we will be transforming that image into the transform domain. So we are taking our special domain information into the transform domain with the help of DCT transformation. Now each block is compressed through quantization. Once you get the DCT transformation, so DCT, that is discrete cosine transformation, gives us the frequency information. So basically we get a DC component and we get the AC component. Now these AC components, in each DCT block, the 0, 0th number of block contains the DC value of the entire 8x8 pixel values. And then as you move away from that DC value in a zigzag manner, the frequency increases. Means what? You are going from low frequency to middle frequency to high frequency. Now generally, if you just remove the high frequency information from that DCT part, it will not impact much on the information or during the retrieval process. So that is the basic concept of JPEG compression and why we are using DCT in the JPEG compression. That's what we are going to see. So this is what we are doing. So each block is compressed through quantization, and then array of compressed blocks that constitute the image is finally we are applying a source coding method, that is Huffman coding is applied in the zigzag pattern. So this is the process that we are going to see. Now before we just go into the exact steps and the image point of view, let's just see the basic equations which are used for DCT compression. So this is the this is the DCT equation, DCT compression, which is applied on each 8x8 block, and this is the equation which we need to apply. So with the help of this DCT transformation, each 8x8 block is DCT of that 8x8 block is obtained, find out, and you will get the transformed value of individual blocks. So you can say that your entire image is transformed into the DCT domain. Okay, so this is what we get. So this is the equation that we had seen in the last slide. So that equation, if you just apply on 8x8, if the total number of pixels that we are considering is 8x8, then this is the standard matrix that we are getting. So using this equation, if you put different values of, let's say 8 cross 8, so the total values will be 8 cross 8 block for individual pixel. If you just put the values of X and Y, then you will be getting a DCT matrix, and that DCT matrix is something like this. So this is the DCT matrix which we will be using to transform individual pixel values or your entire image into the DCT domain. So this is one standard DCT matrix that you can obtain, and this is also mathematically you can prove, and you can find out and you can verify the values with the previous equations. So this is the first thing. Now, how to compute the DCT of each block? So before we go for the DCT, okay, so what we need to do is you need to convert the pixel values within the range of signed components, because we know that when you apply the transformation, you will be getting the positive and negative values. So therefore, what we are doing is rather than using 8-bit unsigned values, we will be using 8-bit signed values. So now the range will be minus 128 to plus 127. Okay, so this is done by original block is leveled off by subtracting 128 from each pixel of block. So this is the first step. So because DCT is designed to work on pixel values ranging from this, each individual block is subtracted, is now leveled off by subtracting 128. So what we will be doing, we will be subtracting 128 from each pixel value of individual blocks. And then whatever block we are getting, in that block, we will be finding the DCT using this equation, that is TMT dash. Okay, so what is TMT dash? T is basically a DCT matrix, that is this one that we have already obtained. This T will be multiplied with M. M is what? M is the block which is subtracted by 128, and then it will be again multiplied with the T dash, that is transpose of DCT block. So this is the DCT. This is how we compute the DCT of individual block, and we get the value of D. So this is our first step or second step. Once we have the DCT matrix, this is what we will be doing. So the first step is entire image is converted into 8 cross 8 block. On individual block, we will be finding DCT using this equation TMT dash. Once we get the value of DCT of individual block, this is what the result will be. Let's say, let me just show that part. Let's say this is one entire block. So I am having one image of 256 cross 256. I am just dividing entire image into 8 cross 8 block. So this is just one block of 8 cross 8. I am just showing one particular block of an entire image, that is 8 cross 8 block. Now, before applying the DCT, we need to level off this block by subtracting 128. So from individual pixels, 128 is subtracted. So 154 minus 128 will give 26. 123 minus 128 will give minus 5. 154 minus 128 will give 26. 239 minus 128 will give 111, and so on. So now you can see that this is the labeled off matrix M, which is obtained from the original block simply by subtracting 128. So this is what we will be having. So now your pixel values are also in the range of minus 128 to plus 127. Your DCT matrix is also in the range of minus 128 to plus 127. So now after this, we will be simply calculating the DCT of this block using the equation TMT dash. So this is simple matrix multiplication and matrix transformation operations. So different simple algebra, you just apply them and you calculate the value of D. So this is the DCT of one block. So similarly, you find out DCT of every block in the entire image. એટલે માની લો કે તમારી પાસે એક image છે 256 cross 256. So you will be having 8 cross 8 block. For individual 8 cross 8 block, you calculate the DCT. You calculate the DCT transformation. You calculate the DCT transformation. Okay. Now let's move further. Once you calculate the DCT transformation for each block, okay, once you have got the DCT of individual block, what we need to do is you need to just observe the values. So in each block consists of 64 coefficients because it is 8 cross 8. So total 64 pixels are there. Now total 64 DCT coefficients are there. The top left coefficient is C00, and this C00 correlates to the low frequencies of original image block, as I told you. the 0th value of individual block is the DC low frequency value. And as we move away from it in all directions, it correlates to higher and higher frequencies of the block. Okay, so as you move away from the DC value, then the frequencies are increasing. One can say that the DCT coefficient represents values for low, mid, and high frequencies present in the block. Okay, so now individual block is having three kind of frequency informations: low frequency, mid frequency, and high frequency. So as per our previous discussion, if you want to do compression, then you simply remove the high frequency elements and then you can simply have a compression. So C00 is the DC component. We will not do anything with this DC component, because if you will change the DC component, then the brightness and the contrast and everything, the information related to that block will be highly affected. So we will not do anything with that DC component, but the other AC frequency components should have some redundant information and we can remove them. So as we move away in zigzag pattern, the coefficient represents low frequency, mid frequency, and high frequency, and C77 correlates the highest frequency coefficient. So whatever is explained in this particular slide can be visualized in our information in our result also. Okay, so what we are saying is this was our data. So as you can see that in this DCT matrix, this is C00. So this C00, the value is 162.3. This is the DC value of this entire block. We are not supposed, most of the energy of this entire block is stored in this particular pixel value, that is C00. Now as you move in the zigzag pattern, so 40.6, 30.5, minus 94.1, 108.4, 20, then 72.3, 10.5, minus 60.1, minus 38.6, then minus 31.3, minus 83.4, 12.3, 32.3, 30.3, then 12.5, 27.7, and so on. This is how the zigzag pattern goes on. So if you go away in this, if you move in this zigzag pattern, as you move away from the DC value, the frequency is increasing. So initial components are low frequency, then there will be mid frequency, and as you go away, there will be high frequency components. So this C77 represents the highest frequency component. So 10.7 is the highest frequency component, and this 40.6, 30.5, these are the nearer low frequency components. So basically, the entire DCT block contains four information. Number one is DC value, low frequency values, mid frequency values, and high frequency values. So this is what this particular slide wants to say. So now we know that your image was actually in the spatial domain was only having pixels. In the DCT domain, you have obtained frequencies, and from frequencies in an individual block, you can identify what are the low frequency components, which are high frequency component, which are mid frequency component, and which are and what is the DC value, and you can work on it. So now the next part of the encoding algorithm is quantization. So once you do the DCT transformation, you know that already the compression, the transformation is done, which values are to be eliminated, that is also known. So now you need to do the quantization. So now as the quantization step is involved, we can say that JPEG compression is a lossy compression. It is not a lossless compression, but it is a lossy compression. So that we need to analyze. Now the quantization is done using quantization matrix. So as per the required compression, quantization matrix is generated. So how the quantization matrix is generated? There are different quality metrics, you can say, in case of JPEG compression, like you want to do a compression of quality factor 10, 20, 30, 40, etc. So that's why you can vary your JPEG compression levels, and that is depending on this quantization matrix. Okay. So how to obtain this quantization matrix? So Cij, that is the Cij is equals to round off Dij upon Qij. This Qij is basically a quantization matrix. So your individual block is having total of 64 DCT coefficients. So you generate a quantization matrix of also 64 coefficients, and then individual pixel by pixel operation is done. That is division operation, Dij upon Qij, and rounding of that. So that will give you the Cij components. That is basically a quantization result. So how the quantization matrix is generated? So this is one standard quantization matrix which you can use as per JPEG standard. So 50% quantization matrix is this one. So this is one standard matrix. which you can use. And now if you want a quantization level more than 50%, if you want let's say quality level less than 50%, more than 50%, accordingly you need to change this. So if I want only 50% quality level, then I know that I am already having this D. Now this is having 64 coefficient, and this quantization matrix, quality matrix with 50% is also having 64 coefficients. So what is the equation now for quantization? Rounding of Dij upon Qij. So what is D00? D00 is 162.3 and Q00 is 16. So simply rounding off by 162.3 divided by 16. Whatever will be there, that is the value that will replace at the 00th value. So that is how the simple quantization is done. Now, if you want a quality factor greater than 50, then you simply have to do this 100 minus desired quality level. Let's say if I want 51, 52, 53 or 100, then this is what you need to do. So if your quality level is let's say 99, then 100 minus 99 divided by 50. So this is what you need to do with respect to original quality matrix. So if you are having this standard quantization matrix, as per if you need more than 50% of quality, then just simply modify this quality matrix using this formula 100 minus desired quality level by 50. And similarly, if you want a quality level less than 50, then simply use this formula 50 divided by the desired quality level. So now, as per your requirement, you can fine tune the quantization matrix. એટલે કે તમારું standard quantization matrix જે છે 50% quality level, that can be modified as per your requirement. It can be 10%, 20%, 30%, 25%, 70%, 75%. You just need to use these two formulas. If your quality level is more than 50%, use this formula to modify the quality matrix. If it is less than 50%, use this formula to modify the quality matrix. Okay, this is how we will modify Q. And once you have the Q, you simply have to do the process that is Cij. So now, as per our previous term, we have already obtained Dij. We already have the Qij, that is Q matrix and D matrix. D is basically a DCT matrix. Q is basically a quality matrix. And now using both the matrix, we will generate Cij, that is quantization result. So this is what we are having. Now you can see that once you perform the quantization in the entire 8x8 block, most of the values are 0. So as you move away from the DC, so this DC value is 10. As you move away from it, the values are becoming negative, and then ultimately many values are going to be 0. So this is low frequency, mid frequency, and as you move further, most of the high frequency elements are 0. So that means these values are not required to be transmitted. So previously there were 64 values and each having 8 bits. So that was 64 bytes of data was required to be transmitted for each block. But now most of the values are 0. So those many bytes are saved. So this is a kind of compression. So if you do more quantization, again you can have more number of zeros, and that's how the process goes on. So this is a very simple quantization process. So once you have this matrix, then you simply have to perform source coding. So we are in JPEG compression, the source coding method which is used is Huffman coding. So in the Huffman coding, we know that individual pixel value, it is basically a source coding method. So individual variable bit length is obtained using Huffman matrix. So for this entire data, we find out the probability of occurrence of each values, and then we simply perform the Huffman coding. But this Huffman coding is done in a zigzag manner. Means you need to find out the code for 10, then you need to find out the code for 4, then 3, then -7, 9, 2, and so on. So as you can see here, the code is obtained like this, and then the codes for individual bits are transmitted. So once you get this, now you have the bit stream 10, 4, 3, -7, 9, 2, 5, 1, -5, -3, -2, -5, 1, 2, 1, 0, 1, -2, 0, 1, 0, 0, 0, 0, -1, -1, 0, 0, and then rest of all are zeros. So now for this particular bits, you simply have to perform Huffman coding, find out the codes, and then transmit them. So this is what the Huffman coding is. So that Huffman coding part already we have discussed in the previous sessions, and you all must be knowing that from digital communication point of view also in the previous subjects. So you can simply perform the Huffman coding, identify the binary codes, and then you simply transmit them and make a bit stream and transmit them. So this is how the final encoding encoding is completed here, the source coding part, and then it is transmitted. So this is what we are doing at the transmitting end. So once you simply revise it, it is a very simple process. You take an image. In the entire image, you first of all perform 8x8 block. So that's what is done. You take a standard DCT equation, made 8x8 DCT equation. This is a standard DCT matrix. Then for individual block, you simply find the leveling of matrix. In the leveling of blocking is done, that is simply obtained by subtracting 128. Then for individual block, you perform the DCT and obtain DCT block, that is using the equation TMT dash. After finding DCT, you find out quality matrix. So quality matrix of desired quality level is obtained using this. If you want to change the quality higher than this, lower than this, then accordingly you just perform the operation and just change them. The quality level is changed. So the new quality matrix is obtained, and then you simply perform the division operation to go for it. So then you will be having a compression. Rounding off is done, and then in a zigzag manner, you just simply find the Huffman coding and generate a bit pattern which is to be transmitted. So this is how the JPEG compression is done. Now, if you want to reconstruct the original data at the receiver, because most of the values are 0, and how the original matrix is reconstructed. So very first thing at the receiver side that will be done will be whatever value you are getting is CIJ. CIJ means this matrix is there. You already know how much compression was done. That is required. That should be known to you. How much compression was done. So let's say if you know the compression matrix, so that QIJ matrix is known to you. So you simply perform the multiplication because the division was done. So the reverse process is multiplication. So once you do that, this is the R matrix which is there. Now, as I told you, this is a lossy compression. So most of the values, even after the reconstructions, are 0. And why it is so? Because this is quantization. And once it is quantized, you cannot reconstruct the original values. So in individual block, originally there were 64 DCT coefficients. Now, the most of the high frequency DCT coefficients are 0, even in the reconstruction part also. But if you reverse the process again with this, the reverse process is this one, rounding of T dash RT. So you just simply perform the multiplication of T dash RT. That is a reverse process of matrix multiplication that we did for DCT. So this is inverse DCT coefficient. That's what we are doing. So now you simply perform inverse DCT. So inverse DCT is done by T dash RT. T and T is simply the DCT matrix that we already there. So you just simply perform T dash RT, and then you add 128, which was originally subtracted. So this is the original block which is obtained. Now you just compare this block with the original one. So this is the original block which was there, and the block which is received at the receiver side is this one. There is some difference in all the pixel values, and this difference is there because it is not possible to generate and reconstruct the original information as it is. Why? The reason is only one. It is a lossy compression, and as it is a lossy compression, it becomes impossible to reconstruct the original data. So this is how the reconstruction is done. So in case of JPEG reconstruction, it is very simple. You should be knowing the quality matrix. So whatever matrix you are getting at the receiving side, then you simply multiply the quality matrix. And once you do that, you need to perform the IDCT, that is inverse DCT transformation. So that is T dash RT. And then you add 128, which were subtracted to level off on the original case. So that is done, and you will be getting the decompressed image. So this is what the deconstruction is. These are some of the results that we are having. The original image is this one. You perform the DCT, the matrix which is obtained is on the second side. These are the MATLAB results that we have generated. I am just showing you the MATLAB results directly. So original image, the DCT matrix. After quantization, we get a result like this. And then using 50% quality level, then there are 80% of high frequency components are 0. But still, this is the result that we are getting after compression. So you just see, compare both the images, image 1 and image 2. So for a normal human person, normal applications where we just need to identify the objects and all that, and just to transmit the information in our internet, web, like Instagram, like Facebook, WhatsApp, and through other internet sources, you need to have a small amount of data to be transmitted. And in that particular case, this is much more easier, and this is feasible option. So this is what the image that you are having after compression. And all of you also know that if I'm taking a high definition HD image, it is of 5 MB to 10 MB. and when I compress them to JPEG, it becomes almost of 50 KB to let's say 1 MB. So that's a whole lot of compression that we are doing with JPEG. And if you just simply see them in a normal frame size, okay, then it becomes very difficult for a normal person or for us to identify the difference between them. So that's what the JPEG compression is. So that was the JPEG compression. These are the other values we are having. The original image, this is 10% quality level, this is 20% quality level. The result that we had seen here was 50% of quality level. So as you reduce the quality level, the compression will be more and more. And you can just see the result of this 10% and 20%. There are some blocks that you will be identifying here. So here there are a few blocks. Why these blocks are there? Because it's a block level transformation. So just because of the block level transformation, you will be having the effect of blockiness if your compression is much higher. Because here you are only preserving 10% of information and 90% of information is removed. So that's what the compression is. So this is what we are having. And thank you so much. So I hope this lecture was good enough for you to understand the basic process of JPEG compression and JPEG decompression. Thank you so much.